Hello everyone, my name is Rafi Shalom and I will be presenting our paper, Unrealizable Cores for Reactive System Specifications, a paper of Shahar Maoz and of myself. We begin with a short demo. Here we can see a GR1 specification. GR1 specifications have assumptions and they have guarantees. Each may have assumptions on the initial states, assumptions on transitions, and justices, which are assumptions about things that occur an infinite number of times within a run. If we look for the realizability of this specification, we can see that it is unrealizable, which means that there is no implementation that we can synthesize from this specification. The way to localize the problem is computing a core, an unrealizable core. If we compute a core, we can see that we have a core with 3 guarantees. This means that even with these 3 guarantees, the specification is already unrealizable. And if we further remove guarantees, the specification becomes realizable. However, there can be many cores within one specification. And if we compute all the cores, you can see that we have 6 cores and that there is one element that belongs to all the cores in line 30. There were 3 limitations of previous approaches. The first limitation was that computing a single core was slow. It was done with delta debugging by us and by others. The other limitation is that there was no effective algorithm to compute all the cores. And the third limitation is that there was no effective support for specifications beyond pure GR1 specifications. Previous solutions were buggy and inefficient. For this, we have 3 contributions. One is QuickCore, which computes a core quickly. Another is the punch algorithm that computes all the cores and evidently finds the smallest core, and our algorithm also finds the intersection of all the cores without computing all of them. We also have an extension for specifications reducible to GR1, which is also applicable to other domains, but we won't get into it here for lack of time. Let us now discuss the QuickCore algorithm. The QuickCore algorithm is based on 3 key ideas. The first idea is that cores can be computed incrementally, group by group of guarantees. The second idea is that removing justices makes realizability checks much cheaper, which means that we would like to remove as many of them early on in the computation. The third idea is that when minimizing only initial assertions, the winning region can be computed only once. This is how it looks like. We have the QuickCore algorithm. It receives a specification, and it provides us a single core of the specification. We first try to minimize the justices with delta debugging, but we first check if no justices are needed. If no justices are needed, we also remove the assumption justices, the environment justices. Then we minimize the safeties also with delta debugging. Then we compute the winning region only once, and we minimize the initial assertions one by one with linear minimization. And now about the punch algorithm. Punch algorithm first computes a core with any method. Then it goes over the elements of the core one by one, removes them from the total set, and collects either to the set of the intersection of all the cores, or it has to continue finding cores when we remove that element, and we do that recursively. And now for the evaluation. We have 5 research questions. The first one is about which existing domain-agnostic minimization algorithm is best. Before this work, we used delta debugging alone. Questions R1 and R2 are about QuickCore, its efficiency, and its effectiveness in localizing the problem. Question R3 is about how many specifications we have with multiple cores. And R4 is about the efficiency of punch. For this, we implemented many algorithms. The first algorithms are about single-core computations. DD-mean and QuickExplain are domain-agnostic algorithms, and QuickCore algorithm, which is domain-specific. We also implemented multiple core algorithms. TD is a naive top-down research algorithm, which is domain-agnostic. PUD and PQC are two versions of punch. The first is with DD-mean as a core computation, and PQC is with QuickCore for the core computation. The first is domain agnostic, the second is domain specific. With all our algorithms, we use the same memorization that we described in detail in the paper, and we won't get into it here. Now for our corpus. We first have syntax specifications, which are autonomous Lego robot specifications written by third-year undergraduate computer science students and contain many extensions. Scene 15 new are the unrealizable ones from year 15, and scene 17 new is the same from year 17. We also have AMBA and GenBuff, which are well known in the literature. Those are pure GR1 specifications. Both AMBA and GenBuff have 4 sizes and 3 types of unrealizability. So we have a total of 24 specifications, which we denote AM plus GN. The setup is an ordinary PC with a single core. Times are the averages of 10 runs, and use 10 runs because the BEDs add some stochastic elements. And we have a timeout of 10 minutes for computations of all cores, which we denote by TO. Now let us look at the results. This table compares the running times of delta debugging with QuickExplain. Here we can see time frames, let's say from 1 second to 10 seconds, or from 10 seconds to 100 seconds. The time frames are the time required for delta debugging to compute its computation, and the numbers are the geometric mean of the ratio between the running time of DD-mean and QuickExplain. As we can see, the running time of DD-mean is less than that of QuickExplain, and this effect grows weaker as time progresses. This justifies our use of delta debugging within QuickCore and with the comparison of it to QuickCore. We have a similar table for the comparison of QuickCore and delta debugging. And here we can see that QuickCore sometimes is slower than delta debugging for very small specifications, but as the specifications become larger, it becomes much better, even well over an order of magnitude. The third table shows the core sizes, the localization effectiveness. Here we can see that the core sizes of QuickCore are about a fifth of the original set of guarantees. The averages of QuickCore, delta debugging, and QuickExplain are about the same and close to the global minimum. And now for the number of cores. Here we can see that for syntax 15U and syntax 70U, we have more specifications with multiple cores than we have specifications with single cores. And there are specifications with well over 50 cores. Finally, we compared the efficiency of punch to the baseline algorithm TD, and the comparison shows that the baseline algorithm is much slower than the 2 versions of punch, and there's a slight advantage for punch that computes a core with QuickCore. We won't get into the details of this table here, but it's in our paper. We would like to thank you for listening to our lecture about unrealizable cores for reactive system specifications.
Hello, everyone, and welcome back to the second Q&A session. And I hope you've enjoyed the presentation. We have here with us both authors. We have Rafi Shalom and Shahar Mautz from the Tel Aviv University. So you can please, I ask you all to please type your questions in the chat So I can ask both Rafi and Shar if they have the questions. Okay. So just to give you guys some time to type in the meantime that you type in your questions, I will ask a question to Rafi about his about this research work. So in your research, in your presentation, you have specified 5 research questions. So you say that you have identified and implemented many algorithms for the evaluation that you have carried out, right? So I'm wondering, what criteria have you used to define or select each algorithm that you have used to evaluate and to, yes, for the evaluation of your specifications?
All right, so we have two kinds of algorithms. One kind of algorithm is for finding a single core, and the other kind of algorithm is for finding multiple cores or all the cores and their intersection. So for the first part, we have QuickCore, which is a novel algorithm we presented in order to find single cores. Before that, the usual thing to use in our systems was delta debugging, and which delta debugging is domain agnostic, so it's not specifically tied to the domain that we have. But QuickCore uses the domain-specific properties of GR1 in order to accelerate the core computation, which means that we have these two algorithms already. And then on top of that, we added QuickExplain, which is another domain-agnostic algorithm for single-core computations. That was actually by important comments from the reviewers that wanted us to handle this as well, because they thought it would be a good comparison. And that's why we added this as well. For the multiple cores or all the cores, we have our algorithm, which is a kind of baseline algorithm for finding all cores, also domain agnostic. But we just wanted something initial, something that we can use initially. And it can use a single core. It has a component of finding a single core. So we have two versions, one with finding a single core by QuickCore and one by delta debugging, which was found superior to QuickExplain already. And on our domain, only on our domain. We're not talking about generally. And so we compared that also to a baseline, which is some kind of top-down recursive algorithm. We wanted to add some comparison with domain-agnostic algorithms like MUST, but we didn't get to it. It was already a very packed packed paper, so we left it for further research, and we mentioned it in the paper. More.
Okay, thank you. Shad, do you want to comment on that, or can we go to the next question?
You can go to the next question.
Okay, so we have Gary. Thank you for your question. Also, he is asking, so basically he says he's missing some background of your research. So he asks if, could you please explain what a justice assumption is and give an example?
All right, so we didn't have much time to get into it in the presentation. What we have basically is that each part of the players, one is the environment and one is the system, has three kinds of assertions that, that the user can write. And the last one of them is justice. Justice is something that happens an infinite number of times within a run, which means that if, like, suppose you have a traffic light system, and then you have you want to express the fact that you want to have a green light an infinite number of times within the time that the system works. So what you do is you're at globally finally a green light, something like that, and then the system would have a justice which says that the light will be green for that traffic light, and the environment can also have justices as well.
Okay, thank you. Thank you for your answer, Gary. I hope that answers your question. So he
yes,
says,
fairness. Yes,
so it's okay.
Okay, fairness, right?
Yes, but there are many types of fairness. So justice is the globally finally kind of fairness.
Okay. So again, thank you for the clarifications. Thank you for the answer. Thank you, Gary. If anyone has any other questions, feel free to go ahead and ask some. Here we have Renzo asking a question. Thanks for the great presentation. When you compute all the cores, do you always find something in the intersection?
The intersection can be empty. The intersection it could be empty because it's just how it is. So I don't really have to find or may find something within the intersection, but I find all the parts which are all the elements which belong to the intersection when I start to compute it. This is really a very simple proposition. We proved it in the paper, but others use it even without proving it. That when you have a core and you remove one element of from the total set, and then you do the check, and then you can find if it belongs to all the cores or not. So if there are some, we find it. If there aren't, we don't.
Okay, thank you. Thank you again for your answer. So I think we have time for one last question. If nobody asks a question, then I will ask one more question. Okay, so it's more of a curiosity. I mean, how can your research find practical application in a software engineering in a software development company? So lots of interesting stuff going on in there. So like, how do you apply all this stuff? How do you find like the practical implications?
You mean for synthesis in general?
Yeah.
So
Like
right.
if your method of your GR1 specifications.
All right, so there are many applications in which people use GR1. Maybe Shahar can elaborate on that. But whenever you want to create a simple controller and you want to do it from the requirements, so it would be a good tool, and we have many kinds of analysis and ways to synthesize. So, and we're trying to make it faster. Yes.
Yeah, so like, sorry, maybe I didn't ask my question correctly. It's like, why use what you guys are suggesting and not what, I don't know, someone else can find anywhere else?
I can maybe answer that. So currently, nowadays, synthesis already has some applications, mainly in robotics, and in some other domains where the correctness of the system is critical. So in domains like this, where correctness is really critical, there is a strong motivation to use synthesis. And specifically, what we presented is means to deal with unrealizability. That's one very common problem that happens when people try to write specifications that are not toy specifications, not very simple ones. Anyone, even also experts, get to the problem of unrealizability. And then what we specifically presented here is one means to deal with realizability. That's computing a core, which is you can view it as something like a fault localization for unrealizability. So we compute one core or all the cores. That's the main idea.
Okay, so thank you for your presentation, for answering the question. Authors Rafi and Shar. I'm going to wrap up the Q&A session. Thanking all of you, and you can continue in the discussion room. Bye-bye, everyone.